Hello, I'm Seema and welcome to part 16 of the chapter Chemical Bonding and Molecular Structure. In the previous video, I discussed hybridization. I told you about the salient features of hybridization and what are the necessary conditions for hybridization. So, moving on with our discussion, let us now see what is it that gets hybridized, and let us take examples of molecules and see the hybridization of atoms and understand hybridization better. The first question that comes to mind is, what gets hybridized? What is it that gets hybridized? We know that atomic orbitals that combine and they redistribute their energies and result in the formation of the same number of hybrid orbitals. That is what happens in hybridization. But when we have to locate and when we have to see this in a molecule, what is it that we expect undergoes hybridization? Remember that all sigma bonds hybridize. All sigma bonds undergo hybridization, which means wherever there's a bond between two atoms, all the sigma bonds, that is all single bonds, sigma bonds are present in single, double and triple bonds. So all bonds that you see basically, they are participating in hybridization. Then all lone pairs also participate in hybridization. I told you in the previous video that half-filled and completely filled orbitals participate in hybridization and empty orbitals do not participate. So what exactly is participating in hybridization? In order to see that, you must know where the electrons are present, because the first requisite for hybridization to occur is the presence of electrons in those orbitals. So we say all sigma bonds. What is a sigma bond? A sigma bond is a shared pair of electrons between two atoms which is shared by the head-on overlapping of two orbitals. Head-on is the first, the sigma bond is the first bond which is made between two atoms. So all sigma bonds and all lone pairs, they will hybridize. But what about the molecules which have multiple bonds, where you see double bonds and triple bonds? Then what is it that hybridizes? What about multiple bonds? In all multiple bonds, one of them is a sigma bond and the others are pi bonds, right? So one is sigma, and that sigma, as we just saw, all sigma bonds hybridize. So that sigma bond participates in hybridization. But the rest of the bonds are pi bonds, and these pi bonds, the electrons present in the p orbital. How are pi bonds formed? Pi bonds are formed when p orbitals, they overlap sideways. And we know there are three p orbitals, the pz, which is along the internuclear axis, px and py. When pz overlaps head-on, that is the first bond, that is the sigma bond. But I just told you that sigma bonds would participate in hybridization. But, which means that pz is the axis which will participate in hybridization. And px and py, which overlap sideways to form the pi bonds, do not participate in hybridization. You have to remember this. This is very important, that pi bonds are formed by p orbitals, and these p orbitals remain as such. They do not participate in hybridization. So it is only the sigma bonds and all lone pairs which will participate in hybridization. Now we have molecules, and we have to see in a molecule the atoms, and we want to find out the hybridization. So what should we do? The steps here would be, we have to find the places or the regions of density of electrons, or the regions where electrons are present around the atom. What are these regions of density? What do we see in when we see a molecule or a central atom? What are the possible bonds, or where are the electrons possibly present? They may be present as lone pairs. They may be present as the sigma bond in a single bond. A single bond is a sigma bond. They may be in the double bond or in a triple bond. Again, in a double bond, one bond is sigma and one is pi. So it is not the electrons of the pi bond, but the electron density is the two electrons of the sigma bond. That orbital, the one that is the pz, that would participate in in hybridization. And if you have a triple bond, again a triple bond would also contribute one pair of electrons which are present in the sigma bond, while the pi bonds would not participate in the bonding, in the hybridization. So the first step is to identify the regions of electron density around the atom. Do you know the number of regions you have to identify? Let us say there is one lone pair, there is one single bond, there's one double bond and one triple bond. So there will be 4 regions of electron density in that particular molecule. If it has 4 regions of density, then you just identify this number, the regions of electron density, and the hybridization is in relation to that. So if the atom has 2 regions of electron density around it, then the hybridization is an sp hybridization. If it has 3 regions, it is sp2, 4 regions, sp3, 5 regions is sp3d or dsp3. When we say sp3d, it means sp3 and d, sp and d orbitals of the same shell. But when we say dsp3, it means the d orbital is of the penultimate shell. The hybridization is occurring between d orbitals of the penultimate shell and the sp3 of the ultimate shell or the outermost shell. If the number of the regions of electron density is 6, then the hybridization is sp3d2 or it is d2sp3, where again the presence of d will give you an idea whether the d orbitals are of the penultimate shell or are they of the same shell. This is just the numerical part. Theoretically, let us now understand what happens. We take this example of beryllium chloride, beryllium dichloride. Beryllium is the 4th element. So what is its electronic configuration? In the ground state, beryllium has 1s, 2, 2s, 2. And the 2p orbitals, which are slightly higher than the 2s, they are empty, right? 1s2, 2s2, and these are empty. In beryllium chloride, there are 2 chlorine atoms. We see that in order for a bond to be formed, the electrons, they should be present, the orbitals should be singly occupied. One singly occupied orbital of one atom, it overlaps with a singly occupied orbital of the other atom, and when they overlap, that is when bonding takes place. And that pair of electrons belongs to both the atoms, isn't it? That's how we understand a bond. So, when we see that there are no paired electrons in the ground state, but when there are 2 chlorine atoms around beryllium, that is when beryllium, it gets excited. You remember, I told you that empty orbitals cannot participate in hybridization. And also, you cannot have empty orbitals participating in bonding. So whenever such a situation arises, just before hybridization occurs, now there are 2 chlorine atoms. In order to form those 2 bonds, what will beryllium do? Beryllium will allow one of its electrons to jump up to the 2p orbital. So one electron from the 2s orbital jumps up to the 2p orbital, right? This is called the excited state of beryllium. In the excited state, now both the orbitals are singly occupied and they would merge one s orbital, that is the 2s orbital, and one orbital of the 2p, that is 2pz, let us say. These two, they hybridize, and when they hybridize, they result, as a result of hybridization, now 2 of the orbitals are hybridizing, the other 2 of the px and py are empty, so they do not participate in hybridization. Only 2s and 2pz, they participate and result in the formation of 2 hybrid orbitals of equal energy. They result in the formation of 2 hybrid orbitals of equal energy, and now these 2 electrons would be present in the 2 orbitals of equal energy, and both these orbitals, what would their names be? These are 2 orbitals when the, let us first look at this. So what do you have in beryllium in the outermost shell? You have 1 electron here and 1 electron here. So the areas, the regions of density, if you make the structure of beryllium chloride, beryllium is here, and, or let me make the structure like this. This is beryllium. Now it has 2 hybrid orbitals, and the hybrid orbitals, it was formed by the S hybridization of S and P orbital. The S orbital is spherical and the P orbital is the shape of a dumbbell. So you get two orbitals and both of them are dumbbells. The S part is a small lobe and due to the Y part you have one large lobe. And then these two orbitals are directed along since they are two orbitals, what is the maximum distance that they can occupy? 180 degrees. So they are present like this, and then you have two of these orbitals from chlorine, that is the p orbitals. The area of overlap is here. One sigma bond is here and one sigma bond is here. This is beryllium, this is chlorine, and this is chlorine, right? So this results in the formation of BeCl2, where two hybrid orbitals, they participated and resulted in the formation of BeCl2, which is linear in shape. What are these hybrid orbitals called? They are called by the same name. This is one sp orbital and this is the other sp orbital. Why do we call it sp? Because one s and one p orbitals have combined together, have hybridized to give us two orbitals, that is sp and sp. Since they are identical, they have the same name, right? So this was formation of BeCl2. So what did we do? We found the regions of density around the nucleus, and then we realized that since there are two electrons, that is two bonds formed, there should be two sigma bonds around it, and since there are two sigma bonds, the hybridization is sp. And even this way you understand this. Now, boron is the fifth element. It has 5 electrons in all, and 3 of those 5 electrons are in the valence shell. So let us write down the electronic configuration of boron. Boron has 2 electrons in 1s, 2 electrons in 2s, and this is 2p. 2p has 3 orbitals and 1 electron in 2p, right? So this is the electronic configuration of boron in the ground state. In order to have orbitals, now since it is going to combine with 3 chlorine atoms, it needs 3 orbitals to form the bonds, and therefore it needs 3 orbitals which are at least half filled in order to carry out the bonding and to hybridize. So what it does, it gets excited, and just before it undergoes hybridization, it pushes one electron up to the one of the p orbitals. So one electron from the 2s orbital jumps up to the 2p orbital, which is slightly higher in energy, and now these 3 orbitals, they hybridize. And when they hybridize, what do they result in the formation of? They result in the formation of, if 3 orbitals hybridize, they will result in the formation of 3 orbitals which are equal in energy. And what would these orbitals be called now? They would be sp2, sp2, sp2. Why? Because they are formed by the hybridization of 1s and 2p orbitals. Do you see? 1s and 2p orbitals. 3 orbitals combine to form the sp2 hybridization. And now each one has 1 electron each, right? And before this you have this, the 2 electrons are present here, and now in the hybridized atom. And now these 3 orbitals, the hybrid orbitals, will overlap with the 3 chlorines. And what would the orientation be now? Since it's symmetrical, all 3 are equal in energy. Earlier we had an s orbital and 2 p orbitals. You could not have explained the symmetrical triangular shape of BeCl3. But now, when all 3 are hybridized, they all have equal energy, they orient themselves along the 3 corners of a regular triangle, resulting in the formation of BeCl3, which is triangular planar. So how do we make this again? Since the hybrid is made up of s orbital and p orbitals, again the shape of the hybrid orbital would be like this. 2 lobes, 1 large lobe and 1 small lobe. The large lobe due to the p character and the small lobe due to the s character, which as it is a smaller. So we have boron in the center, and we have 1, 2 and 3. Oops, I should have made this bigger. These are the 3 orbitals of boron, and the 3 chlorines, they combine with it here, right? So this is boron and these three are chlorines. I will come to the hybridization of these atoms at the end also, but right now we are focusing on the central atom. So the hybridization of boron here, what is it? It is sp2. So we say boron undergoes sp2 hybridization, and any substance, any atom which is sp2 hybridized, the shape around it would be triangular planar. Anything which has 4 regions of electron density and the hybridization is sp3, that atom would have tetrahedral arrangement around it. With 5 would be trigonal bipyramidal, and 6 would be tetragonal bipyramidal or octahedral. So these are the shapes that you would obtain. One more thing again, let me just reiterate this because I've written it here, that if there's only a single bond, then there's only one sigma bond and it participates in hybridization. Single, double and triple, all bonds participate in hybridization. The only difference is that only the sigma part of it participates in hybridization. The pi part does not participate, and those p orbitals remain intact and they form their pi bonds. So in a double bond there is one sigma and one pi, and in a triple bond there is one sigma and 2 bonds are pi bonds, which do not the pi part does not participate in hybridization. So let us take another example now. After BeCl2 and BeCl2 and BeCl3, let us now take an example like methane. Right? Now carbon in methane, CH4, carbon now is the 6th element, electronic configuration 1s2, 2s2, so that makes it 4, and 2p has 2 electrons, right? This is carbon in its ground state. When it has 4 hydrogens around it, it would try to form 4 bonds, because when it forms 4 bonds, carbon acquires its octet. So, although it has only 2 empty orbitals, why would it use only 2 orbitals? It would like to expand the capacity to form bonds. And how is that done? It allows one electron to jump up to a higher energy level, and we call it the excited state. And remember, this is not a prerequisite. Sometimes it happens and sometimes it does not. So when it comes up here, now we have how many orbitals available for hybridization? 4 orbitals, 1s and 3p. So we have 4 orbitals of equal energy, and these are sp3, sp3, sp3 and sp3. All of them singly occupied, and all 4 of these will now align themselves along a tetrahedron, and the shape would again be the same. A dumbbell with a large lobe which attributes to the p character, and a small lobe which is due to the s character. And now you have these 1, right, 2, 3 and 4, and you can make the smaller lobes opposite it, and 4. Yeah, so this is carbon, and these orbitals are now directed along the 4 corners of a tetrahedron, and the 4 hydrogens have s orbitals, which, and remember, hydrogen never participates in hybridization. Why? Because it has, in order for hybridization to occur, there should be at least 2 orbitals, and hydrogen has only 1 electron in the 1s orbital, and no other orbital of comparable energy, and no other electron either. So hydrogen does not hybridize. So we have carbon with 4 hydrogens resulting in the formation of methane, and this is sp3 hybridized. Another example would be carbon tetrachloride. In carbon tetrachloride, again, the chlorines would be here. So here I would show something similar to a p bond, p orbital, but it's the same thing. The structure is basically the central carbon. It has the same structure. That is, it is sp3 hybridized, and the 4 chlorines, it would form carbon tetrachloride, right? So now let us come to another molecule, that is ammonia. NH3. Now, nitrogen is the 7th element. So let's write its electronic configuration. 1s2, 2s2, and 2p. Since it is the 7th element, it has 3 electrons. According to Hund's rule of maximum multiplicity, it would occupy all the 3p orbitals which are degenerate. That 1 electron would go to each one of them. Degenerate means orbitals which have the same energy. Now, we would expect these 3 to simply combine with hydrogen, because there are 3 half-filled orbitals, and half-filled orbitals can overlap and they can participate in bonding and result in the formation of a sigma bond. But then they would be at 90 degrees. On the other hand, if nitrogen hybridizes and all lone pairs in the same energy level, which is the outermost energy level, this is 1s, this is 2s, and this is 2p. The second level is the outermost shell. So we have 2s and 3 2p orbitals, all of which can participate in hybridization. Right? All of these can participate in hybridization, and when this happens, it results in the formation of 4 hybrid orbitals. One of them 1, 1, 1, and one of them has 2 electrons. That is the lone pair. Right? So one lone pair, this is an sp3 hybrid orbital, which does not, it is a lone pair, so it does not form a bond, it remains as such, and these 3 sp3 hybrid orbitals, they would participate in the bonding. So ammonia would have 1 lone pair here, and now I'll just make lines instead of making the structure, and the 3 hydrogens would combine like this, resulting in the formation of a tetrahedral structure. But since the lone pair does not appear in the structure, it would appear to be a trigonal pyramid to us. A trigonal, it has 3 corners and a pyramid. That's the shape that it will appear to us. So ammonia is a trigonal pyramidal molecule, and the hybridization of nitrogen here is sp3. Interesting, isn't it? So let's take another example now. After ammonia, we could take water. Yeah? H2O. In H2O, now, oxygen is the molecule. Oxygen is the atom. It's the 8th element, the element next to nitrogen. So I just did not wipe this off to make it easier. We'll add 1 more electron here. You see? So now, there are 2 lone pairs in the outermost shell. Both of them would participate in hybridization, and 2 of these half-filled orbitals, they are the ones that should participate in bonding. So what happens? Now 1 electron more here, so you have 2 lone pairs which do not participate in bonding. So oxygen has 2 lone pairs and the 2 hydrogen atoms. The oxygen here is sp3 hybridized. How did you find it? What is the number of, if you see the structure also, what is the number of regions of density? 1 lone pair, 2 lone pair, and 2 sigma bonds. 4 regions of density. So what should the hybridization be? It should be sp3. So we find that it undergoes sp3 hybridization. Right? And since the lone pairs do not appear in the structure, what does the molecule look like to us? It appears to be angular. Right? It is an angular molecule with a bond angle of about 104 degrees. In ammonia, the bond angle was about 107 degrees, and methane and carbon tetrachloride, it was the tetrahedral angle where there were no lone pairs of electrons, and the bond angle was 109.5 degrees. So this was S, sp and sp3 hybridization if you see the orbitals also. We will now be solving a lot more problems on hybridization, but I'll do that in the next video. If you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.